All right, so today at last we come to backprop as a means to train neural networks, and we will also look at a important specific type of neural networks, the one that has become most successful in the last decade, namely convolutional neural networks. All right, but first, why backprop at all? We have seen that a multilayer perceptron, by projecting data nonlinearly to high-dimensional space, can help us find a representation in which we can then represent non-trivial, nonlinear decision boundaries by just a perceptron in this high-dimensional space. But how to train the beast? This is what today is about. Yeah? So what we are, let's see what is given and what is wanted. Given is training data. So we have pairs xi, yi. This yi, if it's categorical, in neural networks we usually use a different representation because if I have classes 1, 2, and 3, if it's truly a categorical problem, then mixing up 1 with 3 is as bad as mixing up 2 with 3. Yeah? So the similarity or not of the numbers does not mean anything. And this is why we typically use a different encoding here. Yeah? So this is usually encoded as a one-hot vector. Let's call it a T here, T for target. And so we have a Ti instead of a Yi. And if this ith observation belongs to class L, then this would be a vector which is 0. It then has a 1 in the lth position, and then further zeros. Okay, let's say this is, for example, the lth entry out of K, if we have capital K classes. Let me use a different letter here because L I want to use for loss. Let's say it's the kth entry, whatever. Good, so we are given training data. As always, we need to decide on a loss function. You remember that way back when we were discussing the Bayes optimal classifier, we had to define a matrix. It told us how bad is it to mix up one class with the other. And we need to make a similar choice today. Here we assume that we are given some, or that we have chosen some loss function. And this loss function has two arguments. It has the true class, again encoded as a vector here. And then we have the output of the neural network. I could call it f, or I could call it nn or something. Let's say this is a function f, which depends on the input and the many parameters. Parameters of the multilayer perceptron or of the neural network. And this is then the neural network output. And then we have the architecture itself. So in what sense exactly does this output f depend on the inputs and on the parameters? And well, generally speaking, this is some deeply nested function. No? Why deeply nested? Because it turns out that if we have a finite budget of perceptrons or of nonlinear units, we can achieve a more strongly nonlinear mapping by concatenating these as opposed to just stacking many of them in a single layer. So when we have a neural network, we generally discern its width. This is the number of perceptrons per layer. And then we have the depth. This is the number of layers. And this is a bit simplistic because we can have more complicated architectures where where the operations are interwoven in a complicated manner, not to mention recurrent architectures. But for simple ones, this is a useful distinction. Yeah? So the width would be how many perceptrons. In our multi-layer perceptron, we could simply count how many perceptrons did we have at any one stage, and then how many stages. And the trend is to invest, given finite amount of memory, you would rather go for depth, for large depth, than for large width. So this is what's given, and what's at test time we simply evaluate our function, but what's wanted at train time is the parameters that will make this loss smaller. Neural network parameters that give us small loss. And the loss usually comprises two terms. On the one hand, it measures how good are our predictions compared to ground truth on the training data, and it may also include a regularizer. So it may include an extra term that tries to stave off overfitting. So formally, so this is what's wanted at train time. So formally, I can write this as saying I want to minimize my loss, or usually the loss is summation over contributions from all observations in the training data. So I want to have the sum over where I compare predictions to ground truth. The first is ground truth, the second one is prediction. And I want to minimize this over the parameters. Now, this is just a formal way of expressing it. When I write argmin, I don't say how to do this in detail, and there's a lot of science and a lot of art involved in doing this well. But what you do today with the feed-forward networks is basically variations over a same theme, and the same theme is a stochastic gradient descent. And stochastic gradient descent in itself is an approximation to gradient descent. It's both faster, and it actually also has a regularizing effect. Stochastic means that we don't, as in usual gradient descent, we don't estimate this gradient exactly, but we only take a small finite subset of the training data to estimate the gradient to one step, then use a new subset, estimate a new step, etc., etc. So what we're looking for in stochastic gradient descent is is to find new parameters. I'm writing W new here. Which are found by starting from the old ones and then using some more or less cleverly chosen step size. And then I need this derivative of the loss with respect to the parameters. And this is evaluated at the training data. So this is at xi, evaluated at certain values for xi, yi, and evaluated at the old parameters. So we're not looking here for some purely symbolic expression. We really want to get out, because we evaluated here conditioned on specific observations and conditioned on our current choice of parameters, we want to get out real numbers here. All right, now because neural networks are nested functions, we need to apply the chain rule, and we can think about how to do this efficiently. And as an example, I will give the neural network or the multi-layer perceptron that we have worked with so far. So we had a first layer where I had a couple of perceptrons, and I'm summarizing these perceptrons in terms of a matrix W1. So this is, let's say, if X is a column vector, then this would be a matrix which in its rows has the representations or the direction of the different perceptrons. Then we need a nonlinearity. And a very typical nonlinearity inside a neural network is the ReLU. So I'm writing small r here for the rectifying linear unit. You remember this was the thing which leaves positive inputs unchanged and sets negative inputs to 0. Now this produces a new vector. This is the new typically high-dimensional representation that I have just created in a nonlinear fashion. And then I have a second set of perceptrons, W2, acting on those, and then another nonlinearity to obtain the output. And this nonlinearity in the final stage, we usually don't use a rectifying linear unit, but we use something called softmax, which will normalize my output. Yeah, so what is softmax? If I have some vector I might have some temperature parameter in there, or I can omit it. So this is like O divided by 1 transpose e to the O. So this would be a vector of intermediate outputs. And here in the numerator, this is just a summation. Yeah? So this is a new vector that I'm getting out here. Or if you want to write it component-wise, I could say something like it's e to the oj divided by sum over, let's say, p e to the op. And this entire thing would then be sigma of O And here I've written down the jth component of it. Okay, and here by writing O, I've just called all of this here small o. Yeah, I said this has been some intermediate output of the neural network. It is called softmax in the literature. It's actually not a good choice of words, because what we get out from the softmax is something like it's not quite a one-hot encoding. It's like a soft or a nearly one-hot encoding, and hence it is actually a soft argmax, not a softmax. Because we don't get out the maximum value, we get out an indication of where in the vector of outputs my maximum value resides. So it's actually a soft argmax, but in the neural network field, people call it the softmax. Okay, maybe we should have a sketch. So in the multi-layer perceptrons, let's go back to last time. It depends on how many classes I want to predict. So if I want to predict just 2 classes, then I can have here in the fine layer just 1 perceptron. Or if I would like to have a more symmetric representation of the neural network, then I would have 2 perceptrons here. Let's do this explicitly. So if I had 2 classes, I would build 2 perceptrons, and then I would have here the nonlinearity, this taking e to the power of and dividing by the sum. So let's say I'm just representing this as a block here, which produces 2 normalized outputs. This is if I want to predict 2 classes. If I want to predict 3 classes, well, I add another perceptron. I make my sigmoidal normalizing unit a little bit larger. And now I get 3 outputs. So these 3 outputs that I find here on the very right-hand side, this would be an approximate one-hot encoding over 3 outputs, and so on. So if I want to predict 1,000 classes, I will have 1,000 neurons in my output layer. And really, people do that. So in the ImageNet challenge, for example, the task is to see if the image contains any of 1,000 possible classes. Not just dogs and cats, but which breed of dog and which breed of cat and so on. So you have 1,000 classes, and these are represented just simply by a 1,000-dimensional output vector. In the ImageNet example, you put in an entire image, and at the output you have 1,000 neurons, and hope that one of them will fire much more strongly than the others, and then this is the class that you believe is present in the image. All right. So what I've done here is just written in formula the multilayer perceptron that we looked at last time. If this was too fast, maybe let's have a sketch. To have the multilayer perceptron match now the way I've written the formula, this time I'm going to put the input to the neural network on the right-hand side and the output on the left-hand side. And I can draw the multilayer perceptron by saying we had, in the example we considered, these were 2 inputs. And then in the multilayer perceptron we painted last time, there were actually just 2 perceptrons in the first layer. Both had a nonlinearity. And so equivalently, I could say that this here is the input x, and then what we have at this stage here is a linear operation on the x. This is what I've written in the formula as W1 times x. Then come my nonlinearities, which I've here chosen to be ReLUs. So at this stage, I would have a rectifying linear unit of W1 times x. And now come my second layer perceptrons. So that's again a linear operation. So I can write this is W2 times the output of the rectifier, which had W1x as input. And now I had the softmax, which is actually a little bit complicated to draw. Because we normalize by all outputs. I should do something like this. Yeah, so it's somehow a big box which has two outputs. This is how strongly my neural network believes that class 1 or class 2 is present here. So at this stage here, this would be sigma of W2, which was a linear operator acting on the rectifier R, which had as input W1 times X. Okay, so this is now the final output of my neural network, what I've previously called some function f. And f depends on its input x, and it depends on all the parameters. So here the parameters would be W1 and W2. Or I've previously, here I've written them as matrices, or previously I've just summarized them in some parameter vector, W. Yeah?
Usually one activation function associated with one neuron. I'm a bit confused.
Okay. Yes. This is because if you look here in the denominator of the softmax, so what the softmax does is it divides output component J by the sum of all outputs. And this is why this is such a highly connected thing. Okay? So you're right. So usually we have as activation just something acting on the output of a single perceptron. And in the final layer, as far as I know, it is customary to just have the softmax and not something like the ReLU and then the softmax. Any corrections to that, Manuel?
Yes, so because the output of the final layer is, in the case of regression, what the output something in R. In the case of classification, you're basically outputting the so-called log-ins, which is then again R, but you want to squash them into 0, 1, which is why you put everything through the softmax or the sigma. But if you were to have a ReLU before that, you would basically arbitrarily throw away half the area and say that everything needs to be large positive values, which doesn't make sense for the output layer.
Yeah, that's a good argument. If we did put a ReLU just before the sigmoid, we would only get positive outputs, which we don't necessarily want. Thank you, Manuel. Okay, so the typical architecture, you see everything in literature, but the typical architecture would have always linear operation, ReLU inside the network, and then at the very end, if you want to do classification, just the softmax. All right, good. Now, so here's the same picture as we had last time, except that today we use 2 neurons rather than 1 neuron for the output, and that we use the softmax. But this is basically the same picture as last time, just drawn from right to left instead of the other way around. And here is the same thing written as a formula, as a nested function. And now we wanted to find, to do gradient descent, we wanted to find the partial derivative here, or the derivative of this loss function with respect to the parameters. So if I want to write the loss function, I can further say that there's an L here for loss function, and then I would have the true output associated with that input, and then the output of the neural network. And we now want to find this derivative, so let's write that down. So I'm interested in dl by, let's say, dw2 at first, and I should repeat what are all the arguments of L here. We had T, and then sigma of W2 applied to R of W1x. And by the chain rule, I cannot do that in one step, but I should first look at dl of, so we should first see how does this change as we change the second argument of L. And then we can say, all right, and the second argument of L, so W2 R of W1x. How is that a function of the input of the softmax here? And then I can ask, how does that depend on W2? So this is just a recursive application of the chain rule here. And now the interesting thing is that if we ask for d by a W1 of the loss function, then the very first term will be the same. Yeah? So this term would be identical. This term would also be identical. And only in this term would we then start to do something different, namely, what is d W2R of W1x? Then we would ask now, what is this partial with respect to the RW1x? And then we would go on okay, so just the chain rule formally, but the important part is that these computations here are identical. And hence, instead of recomputing them several times, we want to recycle them or reuse these computations. and reusing these computations, that's the essence of backpropagation. All right. So backpropagation. I've given two references here. One is this book by Goodfellow and others, which is very good, or a specific paper from which I'm going to use figures further down. These references and the figure are again in the public document that you know. And following this paper here, I will start by arguing automatic differentiation. What is it? What is it not? So, what is automatic differentiation? By the way, so these same two letters, they have two explanations. There's automatic differentiation, or there is algorithmic differentiation. And they mean the same thing. Okay. So first of all, it is not numerical differentiation. What would be numerical differentiation? If I have this output of my neural network, which depends on parameters, then in numerical differentiation, we work with finite differences. We say that we try predicting or looking at the output at w plus h. If w is a vector, then h is also a vector, of course. And we're looking at f of w evaluated at the original parameter, and then we divide by h. And if we make h small enough, and if our numerics are good, then this will be a decent approximation to the derivative at some point. So I should maybe say that this is evaluated at perhaps w old, and then we would use w old here. It is also not symbolic differentiation. Symbolic differentiation is what we would get from computer algebra. So, for example, if I say symbolic differentiation would give me, if I differentiate the ReLU function r of x by x, where this here is the rectifying linear unit, then a symbolic method would give me the answer that it's 1 if x is non-negative and it's 0 otherwise. And of course, if we have something that has many ReLUs in there, then we quickly get an explosion of cases. This could be positive or negative, and its input could have been positive or negative, and that input could have been positive or negative. So we get this tree which grows very quickly with the depth of the network. And then given this symbolic complicated expression, then we could still evaluate it at some parameter, whatever, x old that we decide, but the expression in between could be huge. In particular for deep networks, just unworkably large. And so what automatic differentiation or algorithmic differentiation does is it applies the chain rule. to obtain a concrete numerical value for the derivative at some point. So how does it do that? It starts by building, so 3 steps essentially. It starts by building a computational graph. And this computational graph is usually made up of very, very basic operations. And if we want to take a shortcut, because we can compute by hand that actually the derivative, some terms cancel and something simplifies, then this needs to be coded in by hand. So this computational graph can either be built beforehand. That's what happens in the older computational frameworks. Old in this field means like 3 years old. TensorFlow, for example. Or it can happen on the fly, as happens in the newer frameworks, such as PyTorch. And this computational graph needs to include for each node a recipe that tells us how to send gradient back through that node. I'll give an example in a moment. So including a recipe on how to differentiate a node with respect to its inputs. Such a recipe we need for each and every node. So for example, if we have here A of x coming together in the neural network and B of x coming together, and they are here being multiplied, and the result is being passed on, then I might now have the information that whatever came out, it would have been good if the result had been even bigger. Yeah, so let's say I've, maybe this is already the output of the neural network. I've put this output into my loss function, and my loss function told me, yeah, the prediction was not bad, but it could have been bigger still. Now, actually at this stage, I don't know, these multipliers A of x and B of x, were they both positive or were they maybe both negative? And of course my reaction how to change them will depend on, were they actually positive or negative when they produced that result in the first place. So when I have dA of x times B of x by dx, let's say, then the product rule tells me that it's the sum. And so if somebody told me that the product of these two terms should go up, then this tells me how I should pass on that information, or how I should, if I'm insatisfied with the result, in a way, how I should distribute the blame. Yeah? So, for example, if these multipliers currently at the given value of x this is always at some concrete value of x. Let's say this is at x equals x old. And perhaps, if I find that A was 1 and B was 100, then this formula tells me here what the leverage will be. So every change in A of x by x will be weighted 100-fold, given the concrete values that I had at that point in time. So, in other words, if I now want to pass information back from the right to the left, I need to know what were these values that were used in producing that output. And in the language of automatic differentiation, this is called the primals that need to be stored here. So first, the computational graph is being built. Then the expression is being evaluated in the forward direction. And the intermediate results need to be stored. And then finally, the gradients can be accumulated in the backward direction. Accumulate gradients in the reverse direction. Using the recipes at each node and the stored primals in each node as needed. All right, and this recipe here of storing the primals going forward and then accumulating them on the way back, this is actually reverse mode automatic differentiation. There's also forward mode. And this reverse mode automatic differentiation, that's the very same thing as backpropagation. So think of it as application of the chain rule plus recycling of results. Yes?
Point 2 and 3 again.
Okay, can I read point 2 and 3 again? 2, it says evaluate expression in forward direction, store primals at each node. And 3 says accumulate gradients in the reverse direction using recipes and stored primals as needed. Too fast? All right, and now I have a figure from this paper that I cited earlier, which is also in the public document. And what we can see here is a computational graph. There are different conventions on how to generate a computational graph. So here, for example, so because we have operators and we have results. And some computational graphs that people draw have just the operators and the results are stored in the arrows, or vice versa. The nodes are the results and the operators are stored in the arrows. Here in this example that they use in the figure, the operators are, okay, let's look at this. So we have x1 here, x2 there. So what then the value at first is just copied, and then the operator here sits on the operator sits on the arrows, let's say. Yeah? Then we get some result out, this V1. Well, actually, maybe I can, let's see if I can put it here. Then this would be then we have something that takes the product of x1 and x2. That's this thing here, product. Then the two are being added up. That's the summation here. There is also a sign being computed, the sign of x2. And then the two results, one is subtracted from the other to give me the final output. And now we can, as always, apply the chain rule. And the thing is, minus. Let's do this. If I write out the chain rule, I get lots of factors as we had here. And each of these factors that you see here in this equation is associated with one set of arrows in this computational graph. What we have here is not the proper computational graph, but for example, let's say how the output of my softmax changes with its input, that is associated, well, with this node here. And if I now want to compute the derivative of the loss function, which is at the very output with respect to the input, then I am multiplying these terms here. And each of these terms is associated with one set of edges in my computational graph. So in other words, if I now want to differentiate this with respect to the input, I can multiply all of these terms that are associated with the edges to obtain my complete derivative. And we will just work through this example after the break.